Welcome to Clinical Chemistry 1, Module 2. This week we're going to talk about analytical techniques and instrumentation used in the clinical chemistry laboratory. The first and foremost, probably most widely used measurement in the clinical chemistry laboratory is spectrophotometry. We're going to do a lot of spectrophotometry labs throughout Chemistry 1 and Chemistry 2. So if at the end of this lecture you're not completely clear on how spectrophotometry works, you will be 150% clear at the end of Chemistry 2, which obviously you'll be 100% clear of it in the next couple weeks. But sometimes it takes doing to understand what this is all about. So don't fear, we'll be doing a lot of spectrophotometry moving forward. What spectrophotometry is the measurement of intensity of light at selected wavelengths. It isolates wavelengths using prisms or diffraction gratings, and the energy of light is inversely proportional to the wavelength. Ultraviolet light at 200 nanometers has greater energy than infrared at 750. In case you were curious, the human eye responds to wavelengths between 380 and 750 nanometers. So we're actually able to see this range. And as you can see, you have different colors as you go through. The blue is on the 400 nanometer side and red is on the 750 nanometer side. With spectrophotometry, if white light is diffracted or partially absorbed by a filter or prism, it becomes visible as certain colors. The color of light seen in the visible spectrum depends on the wavelength that is not absorbed, that is transmitted. Okay, so what is transmitted through something is what's actually seen. When white light is passed through a solution, part of this light is absorbed and the remaining part is transmitted. So if you think of it this way, the darker the solution, the more light is absorbed. The more light or clear the solution is, the easier it is for light to pass through. Keep that in mind as we move forward. Solutions contain particles that absorb certain wavelengths and transmit others. For example, a blue solution, such as blue raspberry Kool-Aid, appears blue because the particles in the solution absorbed all the wavelengths except blue. Blue is the only color seen or transmitted from that blue raspberry Kool-Aid. So when we use spectrophotometry, we talk about something called Beer's law. This is the relationship between absorption of light by a solution and the concentration of that solution. It states that the concentration is directly proportional to the amount of light absorbed and the intensity of the color is proportional to the concentration of the substance. Here's where I'm going to use an analogy using the actual title of what this is, Beer's law. Okay, so what I just read, you probably went in one ear and out the other and you're going, oh my God, what the heck is she talking about? The concentration is directly proportional to the amount of light absorbed. Let's take two examples. If you're not a beer person, I apologize. I'm going to use Guinness and Miller Lite or Bud Light, whatever you want. I'll just say light beer as my example. If you were to take a flashlight and shine it through a pint of Guinness, how much light is going to make it through and out the other side of the glass? Not much. It's very thick and dark. If you take that same flashlight and that same cup filled with a light beer and shine a flashlight through it, a lot of light is going to make it through. So let's read this again and see if it now makes sense. The concentration, or how thick that beer is directly proportional to the amount of light absorbed, and the intensity of color is proportional to the concentration. So the darker it is, the more concentration there is. There's more alcohol, more beerness to it than say a light beer is. It's inversely proportional to the logarithm of transmitted light. We define the logarithm function to be such that when it applies to the number that is 10 raised to some power, then it literally just gives us the power and the base 10 disappears. Log 10x equals x. Well, what the heck? Why do we care about any of this? Well, we do use this when we talk about light being transmitted and light being absorbed. The percent transmittance, or remember the flashlight, this is essentially how a spectrophotometer works. We shine a flashlight through that beer. There's something on the other side of that beer picking out how much light was transmitted through. Okay, so the Guinness didn't transmit very much light at all, so our detector on the other side would say, oh, it didn't pick up much light, it's very concentrated. The light beer, shine the flashlight through, a ton of light made it through, so therefore it transmitted a lot of light. Okay? So if all of the light is absorbed, let's say Guinness, it's super dark black, you'd have 0% transmittance if it absorbs all the light. If no light is absorbed, such as water, if you shine the flashlight through water, it should be 100% transmitted. As the concentration increases, the percent transmittance logarithmically decreases. Okay, so where does all that log stuff come into play? Here we go. Well, the spectrophotometer and the calculation that we use, we don't use percent transmittance to come up with the patient how much of something is in that sample. We have to change it to absorbance. In order to take the amount of light transmitted and turn it into, well, not how much is transmitted, but how much was absorbed by that solution, we have to use this equation. It's not measured directly by the spectrophotometer, but it's mathematically derived from the percent transmittance. So light is shined through your sample. In this case, we're using beer. The light hits the other side. It knows the percent transmittance. Luckily, we have spectrophotometers that do this calculation for us, so you don't have to do it. But you hit the absorbance button, and it does this calculation for you and gives you the absorbance, so it tells you how much light was absorbed. Absorbance equals 2 minus the log of the percent transmittance. Okay? If you have a log key on your calculator, that's what this would do. So all I expect you to know is to memorize this equation and be able to plug it in a calculator if need be. I don't expect you to memorize all of this paragraph that we talked about earlier. Okay? The absorbance is directly proportional to the concentration. Okay? So if you have a higher concentration, you're going to have a higher absorbance. The Guinness beer has a higher concentration, so the absorbance is going to be higher. It's going to absorb more light. If you have the light beer, you're going to have a lower concentration, so you're going to absorb less light. More of it's just going to shine through the other side. So Beer's law, sometimes you refer to it as A equals the molar absorptivity times the length of the light path times the concentration of absorbing molecules. So you'll see it referred to that as sometimes too. Knowing that we use percent absorbance, which is figured out by taking 2 minus the log of percent transmittance, if you've got that, you're doing great. All right, so let's look at how the spectrophotometer thing works that I've been talking about for the last 10 minutes here. It measures the light transmitted by a solution to determine the concentration of the light absorbing substance. So we have a light bulb, or I called it a flashlight before. It goes through a monochromator, which picks the wavelength. Okay, in this case, it picked a yellow one somewhere right in the middle, probably about 500 nanometers or so. And you're able to choose on the spectrophotometer what wavelength you want to use by turning a knob. The manufacturer of the test tells us what one to use. Don't worry, you'll never have to come up with that on your own. Here's our beer. Okay, the sample solution is in a glass container called a cuvette. We shine the light through. It's picked up by a photodetector, how many photons of light are bouncing off of it, and we have a digital display or meter. Fortunately, we have fancy enough equipment that it turns the percent transmittance into this absorbance number for us. Okay? So, some of the things inside the spectrophotometer, we have a light source. It's usually incandescent lamps, a tungsten light bulb per se. Sometimes there's lasers if you're getting really particular and using some type of research work and things like that. And a deuterium discharge lamp can be used for UV work. Nothing I've ever experienced. So the first step is to zero our spectrophotometer with deionized water. The reason we would use water is to tell it that this is 100% transmittance. All right, monochromators. This is where I talked about you pick the wavelength. You turn a knob, you can turn it to 400, 500, 600, whatever you want. It usually uses a filter or a prism to do so. That's how we pick our wavelength. Diffraction gratings are most commonly used. This is a way of bending the light to get to the certain wavelength that you want. We talked about the container that our beer or solution, whatever it is that we're testing for. In our case, in the medical laboratory, it would be a patient sample mixed with a reagent. And inside of that glass container, we call it a cuvette or absorption cell. That container is usually made out of glass, silica, or plastic. quartz is usually required for UV radiation. They must be very clean and optically clear. If you have any scratches or bubbles or anything in it, it can scatter light. We always use the same calibration of cuvettes for consistency. We have fiber optics or light pipes sometimes to better control the beam of light. And in the end, we have that photodetector. It converts light into an electrical signal that is proportional to the number of photons striking on its surface. It can be a photomultiplier tube, photocell, phototube, photodiode. Notice they all say photo because of the photons bouncing against it. Then we have a readout device. So the electrical energy from that detector, from the photons bouncing against it, can give us an analog or a digital type of readout. Then you could have a microprocessor such as a computer or a printer. In our case, we use our pen and paper to write it down. Some quality assurance needs to be in place, as with anything else. We need to make sure the wavelengths are accurate, there's no stray light, there's a little cap that you'll need to close, and that the linearity is working properly. Rasmussen adjunct instructors and program coordinators should be sending their spectrophotometers in from time to time to become calibrated so we make sure that these things are working effectively. So, I gave you all this information. We talk about transmittance and absorbance. What do we do with these numbers? Well, what we do is we take the unknown. So if we had a patient sample, we put it in the spectrophotometer and it's going to give us a number. Okay, so we'd have the absorbance here of our unknown. Then we would take the absorbance of a standard and multiply it times the concentration of a standard, and that would give us our patient result. So you're going to have to memorize this calculation. This is how you get an answer on a spectrophotometer. And we will be doing this starting week 4. All right, we have other types of spectrophotometers, this may not be one you'll ever come in contact with, but if you work in a very large laboratory that does a lot of metals testing, you may come across it. It's a technique for determining the concentration of metal elements in a sample. For example, aluminum, calcium, copper, lead, lithium, magnesium, and zinc. The difference between this is you still have a light source, I'm on the bottom here, which tries to keep that the chopper kind of keeps it in a line. You have a flame that lights this sample on fire, and it creates a vapor per se. There's an entrance slit with the monochromator, an exit slit, and a detector. So what's different is that you are exciting the atoms. So the emission technique is when an element in the sample is excited with a flame, and the radiant energy given off is measured as the element returns to a lower energy level. So you are kind of lighting it on fire and then letting it come down to ground state. Okay, pretty technical stuff. Just memorize the fact that it's used for metal elements, and that the emission is when an element is excited and the radiant energy given off is measured as the element returns to its lower energy level. Okay, that's what you need to know. Just memorize this paragraph. All right, fluorometry. This one is when fluorescence occurs when a molecule absorbs light at one wavelength and re-emits it at a longer wavelength. Some types of fluorometers used are in hematology, such as a flow cytometer. The measurement of physical or chemical characteristics of cells. It can be measurements are made when the cells pass through, usually single file line, and then it uses flow sorting with electrical or mechanical means. I have pictures, don't worry, to collect cells with one or more measured characteristics. All right, so we use laser-induced fluorometry and particle light scattering analysis that allows different populations of cells to be differentiated by shape and size. So here is what it looks like. You've got the sample coming from the top down, and you can see that light, or a laser, is shining at the cells. Readings are taken from these 3 photomultiplier tubes. You got photomultiplier tube 1 over here, tube 2 over here, tube 3 over here, and depending on how much light scatter is picked up on different areas, it tells you the different type of cell that's there. Cell size is by forward scatter. Okay, large cells, small cells. You've got macrophages or monocytes, and the small cells are the lymphocytes or red cells. Granularity is 90% scatter, so it would scatter light at a 90-degree angle. And that would tell that you may have like a neutrophil or an eosinophil or a basophil, something like that. We can also tell DNA and RNA content from that. You'll get a better picture of this in hematology this quarter. The next one, which is used a lot in chemistry, we use it in the immunoassay type of department, usually when testing for something like hormones. Hormones are in such small quantity in the human body, they're hard to detect. So if we can take a antibody with a chemiluminescent substrate added to it, we can create a light reaction when something's present. So if there's something in a very, very minute quantity, it's easier to detect light than it would be to detect a color. So it is the emission of light when an electron returns from an excited or higher energy level to a lower energy level. The excitation event is caused by a chemical reaction. It's used in immunoassays and DNA probe systems and something called enzyme immunoassay. There's a little bit of a picture here of what's going on and how the light reaction looks. It's a chemical reaction that creates a light, chemiluminescence. We will go into more detail with this in the immunology course. The next one is turbidity or nephelometry. This one detects scattered light. Light scattering occurs when energy passes through a solution. It enters a molecule in a collision, which results in light being scattered in all different directions. So if we have an antigen-antibody type of situation occurring, it's going to create I don't want to say blob per se, but a molecule that will, when light hits it, scatter the light. So the more of those molecules we have, the more light scatter there will be. So nephelometry measures light scatter at an angle to the beam incident on the cuvette. Don't worry, I have a picture. Nephelometry measures light at an angle to the beam incident on the cuvette once again. Here's an example. This is the sample, the yellow. And if you had a sample where there's a lot of antigen-antibody reactions present, and the example we would use that would be for immunoglobulin testing, and there's a lot of particles in here, it's going to scatter light like crazy. So you'll have more light scatter coming out the side. All right, next is electrochemistry. Not only do we use spectrophotometry, turbidimetry, etc., we use electrochemistry quite a bit. It's very fast, and it gives a physician a result super quick. You need to know the difference between an electron and an electrode. An electron is a particle carrying a unit charge of negative electricity. An electrode is something you'd find, let's say, in a battery. Electric conductor, usually metal, used as one of two terminals to conduct an electric current through a medium. What we measure is the electrical potential that could exist between the anode and the cathode if they become coupled. The measurement of the electrical potential difference between two electrodes in the chemical cell can tell us how much of an electrolyte, which is what we're testing for in the human body, might be present. Here's an example of how a kind of a battery works, so you can kind of see how the electrodes look. So a battery consists of two electrodes, usually one zinc and one copper, immersed in a electrolyte solution. Okay, we got solution down here, you can see it. When a chemical reaction occurs in the solution, electrons gather on the zinc electrode or cathode, which becomes negatively charged. At the same time, electrons are drawn from the copper electrode, the anode, giving it a positive charge. The difference in charge sets up a potential difference or voltage between those two electrodes. When they are connected by a conducting wire, electrons flow from the cathode to the anode, producing a current. But in the laboratory, we use a reference solution and the patient solution and get a potential difference. The potential difference will be able to tell us how much of things, depending on the type of electrode we're using, such as potassium, chloride, and sodium are very common ones. Electrolytes we use electrochemistry for. The potentiometric methods, as I have in my box down here. The direct measurement of electrical potential due to the activity of free ions. Some other things that are measured this way, pH, CO2, and the electrolytes is what I just mentioned with the sodium, potassium, and chloride. Then we have the ion-selective electrodes. This is specifically what we see inside the chemistry analyzers, which is the electrochemistry in the chemistry analyzers. Very often used for things like, I'm skipping to the bottom here, potassium, sodium, chloride, calcium, lithium, magnesium, and CO2. It consists of a membrane selectively permeable to specific ionic species. So let's say we're testing for potassium. The membrane potentials are caused by the permeability of certain types of membranes to certain ions or cations, we'll say potassium. And then ion-selective membrane is the heart of the ISC as it controls the selectivity of the electrode. Membranes are usually glass, so they are used for monitoring things like pH and electrolytes. So if they're specific to what you're testing for, whether it be potassium, sodium, chloride, you'd have a different electrode for each type of sample. Then we test for pH on a lot of patients. The pH of the body is very important. We're going to talk about this week 9. You don't want a pH that's too high or too low, and the physician needs to know how to react to a patient depending on what the pH might be. So we use ion-selective electrodes. Usually there's a silver wire coated with a silver chloride immersed in a solution of hydrochloric acid and placed into a tube containing a glass membrane tip. When the pH electrode is placed into a test solution, movement of hydrogen ions near the tip of the electrode produces a potential difference between the internal solution and the test solution. We then test that electrical potential and it comes as a readout on the voltmeter. Here is a picture of what that might look like. You can see the pretty little hydrogen ions here attaching to the outside. So we also have a reference electrode, which we just talked about. Silver chloride, or calomel might be two things that are used. So how the pH meter works: number 1, solution is being tested, okay, this blue solution. Number 2 is a glass electrode coated with a special silica glass and containing potassium hydroxide. Number 3 here is the silver electrode that we talked about, which is Ag, means silver on the periodic table. Hydrogen ions, number 4, are interacting with the silica glass bulb. And number 5, the pH meter converts voltage or potential difference into a pH reading compared to the reference electrode. Conductometry refers to the electrochemical technique used to determine the quantity of an analyte present in a mixture by the measurement of its effect on the electrical conductivity of the mixture. It's a measure of the ability of ions in a solution to carry current under the influence of a potential difference. And in a conductometric cell, potential is applied between two inert metal electrodes. Very similar to what we were just talking about. This can be used for things like hematocrit, which is how many red cells there are in the blood. Erythrocytes act as the electrical insulators because of their lipid-based membrane composition. And another application is used for the Coulter Principle. This is what the Coulter Principle would be. It relies on the conductivity of blood cells being lower than that of a salt solution used. The cell suspension is forced to flow through a tiny orifice in which two electrodes on both sides with a constant current. So my picture down on the bottom, you can see these little green, we'll call those red cells. As they pass through, there's a current running through here. Okay, so there's positive and negative. As a cell goes through, it breaks the current, so that counts as 1. This is a good way to count cells. So they send the cells through in a single file line, and every time that current is broken, it counts. Okay, so one cell goes through, it's 1. Another cell goes through, it's 2, 3, 4, 5. So they send all the cells through, and it's able to take a count of exactly how many cells are there by the pulses of the break in electricity. Next one, which we're going to do this week, week 2, is the migration of charged solutes in an electrical field by way of electrophoresis. Solutes are able to take on an electrical charge by becoming ionized, and they move through a type of, it's kind of like what we're going to be using is like a big jello jiggler. We're going to send a solution through it. So in most cases, we use something like proteins. We can separate by size and charge by sending them through a gel from a negatively charged area to a positively charged area. When we're done, it ends up looking something like this picture you see here. The rate of migration through that gel depends on the electrical charge of the molecule. For example, at a pH of 8.4, proteins are negative and travel from the cathode to the anode. The size and shape of the molecule, if it's really big, it's not going to travel very fast. The electrical strength is important. As you'll see, we're using a battery system, so if your batteries are strong, yours may travel faster than another group who may have weak batteries. The properties of the supporting medium, the temperature, the warmer the temperature, the faster it'll go. Electrophoretic mobility is directly proportional to the net charge and inversely proportional to the size. So if it's big, it's going to travel slow, and if it's small and has a strong charge, it's going to travel fast. Some of the things that this electrophoresis gel that we send things through are made out of include cellulose acetate, agarose, and polyacrylamide. We are going to use agarose in our laboratory, but other types of things may use other types of substances. So in general, these are the stages. We got a separation, staining, detection, and quantification. So here's an example of one that's being done upright. This patient sample here is being added to these wells. This whole piece right here is gel. We apply electrical charge. Here's a negative charge and here's a positive charge. And over time, it's going to travel through the gel, okay, because of the electrical charge. Different molecules are going to stop, as you can see these lines in here, at different areas. We're able to look at where they stop to determine what they may be. Some other electrophoresis techniques we use are blotting techniques. We're able to look at that electrophoresis and detect to see if it's actually what we're looking for. For example, a southern blot is used to detect DNA fragments. A northern blot would be used for RNA, and a western blot is used to detect proteins. Western blot is a very good one for HIV detection. So once electrophoresis is done, we think there's HIV there, we're actually able to do what's called a blotting test to make sure. Not going into a ton of detail on that. The next one is chromatography. Kind of like electrophoresis, chromatography separates things based on their ability to travel through a mobile phase. So it's compared to another component or a solution. They're going to travel together, and depending on how they interact, they're going to stop or keep going. So I'll show you a picture here in a second. But chromatography is a physical process where the solutes of a sample are separated as a result of their differential physical interactions between individual compounds and the stationary phase. The basic components are the mobile phase, which could be something like paper or gas. And then we have the stationary phase, which could be, the mobile phase is like a liquid. The stationary phase is a solid or a liquid. So I've got some pictures coming up here. The chromatographic separations are classified by the chemical or physical mechanisms used to separate it. It could be ion exchange, partition, absorption, size exclusion, or affinity mechanisms. It's usually ion exchange and partition that's used. So here's the picture. I was trying to get to the picture for you guys. What we have in the bottom is a solvent. Okay, it's usually some type of an organic solvent. And just like a Bounty tissue sucks up liquid, so does this paper. This paper that is hanging from this clip. So it will wick up that solution. What we do is we put whatever it is that we're trying to separate on the paper, and as the solvent wicks up the paper, the analyte that we're testing for will start to travel with it. Depending on how it acts in that solution or that solvent, it will stop at certain points and separate. So we'll be able to see which things are present based on where they stopped and where they separated. We will be doing that as well. Might be the beginning of chemistry too, but we will perform that. So just memorize it for now. We will physically perform it later. Other types of chromatography are high performance liquid chromatography, or called HPLC. This is liquid chromatography using pressure for fast separations in a controlled temperature environment. Gas chromatography, which if any of you have bachelor's degrees in chemistry, you have used these. I know I have. A gas chromatography uses mixtures of compounds that are volatile. We send it through a high temperature chamber, and it separates based on their chemical makeup. So they will come out the other end one at a time and be picked up by a detector, which is usually something like a mass spectrometer. So we call it gas chromatography mass spectrometry, GC mass spec we call it a lot of times. Okay, first we separate it by gas chromatography, and then we send it through the mass spectrometer, which figures out its mass, and then we can look at it to interpret the results. There's qualitative and quantitative techniques with this. It's usually coupled with the gas or liquid chromatography. And most commonly where I have seen this used in the laboratories I've been with are for things like alcohol and methanol, isopropyl alcohol, um, and ethylene glycol types of testing. Those are probably some of the more common ones. Some drug testing too. Here's what the readout might look like. If you were to print this out and for the patient who may have taken a certain drug, if they did take that drug, you might get a peak. Like this person may have had, I don't even know if this is something anybody would overdose on, but it was a good picture that I found. Ethyl acetate, there's a big peak. 13 is D4-cymene, there's a peak. So those would be something that the patient would have overdosed on. The last thing I'm going to discuss is osmometry. We're going to talk about this a lot at the end of this course as well, but we sometimes need to check a patient's blood sample to see how many dissolved particles there are. This can tell us things like if they have an alcohol overdose or if they have ethylene glycol overdose. It measures the concentration of solute particles in a solution. It measures osmolality indirectly by measuring one of the colligative properties such as freezing point, boiling point, or vapor pressure. A lot of times we get high results. It could mean ethylene glycol poisoning. So we'll learn how this works in more detail at the end of Chemistry 1. But just know what osmometry is for, to measure the concentration of solute particles in a solution. All right, that concludes our section on analytical techniques.